Welcome to all the auto engine enthusiasts for experimental airplanes. I'm making this video to try to help everybody and share what I found worked and didn't work on my experimental. This is my first attempt at building an experimental airplane, and I wanted to do something different. That's why I picked the auto engine conversion. I started with the Zenith 801, which is a 4-passenger kit-built airplane out of Mexico, Missouri. Was originally going to put a Franklin engine in it, and it decided to go ahead and use an auto conversion. I've got extensive background in machining, and I just figured it would be something I'd like to try. Several things that I thought would work didn't. Several things that I didn't think would work did. I'll share everything so you won't get caught. The Zenith is a SO airplane. The RV is a fast airplane, so the first thing you must decide is your mission. Do you want to take off in 500 feet or less and land in 300 feet, or do you want to go 200 miles an hour? You can't have both. Well, at least not yet. Zenith airplane it is a high wing. It's got fixed leading edge slats. The slats are pretty aerodynamically dirty, but very efficient at high angles of attack. Of course, they funnel air underneath the slats and then blow them across the top of the wing. This airplane basically does not stall. It picks up a sink rate that won't quit, but it doesn't stall. It's also equipped with flaperons. These are full span ailerons and flaps that are tied together. So when you lay in the flaps, you have full deployment, and the mixing device actually lets you move those up and down so you have roll control while deploying the flaps in a full setting. The horizontal stabilizer is basically a huge upside down airplane wing. It's designed for low speed characteristics to give you good crisp handling speed. My horizontal stabilizer is about the size of the RV6's wing. You can clearly see that it's got a lot more camber than most any other plane, which is basically just a flat slab. You almost have to define what your mission's going to be. Do you want to go fast, or do you want to go slow and get in and out of real short strips with very durable landing gear on it and be able to absorb a lot of the bumps? Took me about 3 years and 3,000 hours to build my 801, a lot longer than the kit said it would. Underneath the fuselage is the radiator, almost like a P-51. This is my second attempt. My first radiator was way too small. This one is 19 by 21 by 3 inches thick, built by Alumirad in Kingman, Arizona. Nice guy. Guy does great work. The whole trick to making this thing work is the little kickers on the tail end of the diffuser housing. You see those little 45-degree angles. Before I put those on, it didn't work. This is the entrance port for the radiator itself. All the air is funneled past the lower cowling, past the landing gear, pushed into that hole, and fed into the radiator. The radiator sits inside that housing at about a 20-degree angle. This is my first radiator that I attempted to make work, and it was clearly too small. The Zenith flies at such a slow indicated airspeed, there wasn't enough radiator surface area to carry the heat away. There's several different pictures and dimensions on it. The key thing you want to do when you do your radiators is to put a port at the very top of it so it constantly purges any air bubbles out of the radiator itself. This is that particular port. This is connected with the line that goes to the Moroso expansion tank, which is bolted onto my firewall. All my radiator fittings are 1.25 inches in and out. As much as I could, I ran aluminum thin wall tubing to connect everything and just used high quality rubber radiator hoses to make all the transitions. When I first did the lower diffuser, I kicked it up immediately, tried to get everything out of the airflow, but it turns out that the air was detached off the front cowling and it never got to the back of it, which created negative pressure to draw air through the radiator. In fact, the air went backwards through the radiator and went forward. This is my second attempt. I made it hang lower in the air and it still didn't work. My third attempt right here is what worked. The whole trick is those kickers on the back. Without those, a radiator would not breathe properly. You can see the white hose. That's a garden hose. That is the airflow that I thought would come off the cowling, follow around, and reattach itself to the bottom of the fuselage, which would in effect put the discharge area of the diffuser housing where the radiator sat in a low pressure area. That didn't work. The way the hose is now is the actual true airflow as it came off. Notice that the radiator, top half of the radiator, is actually still in the negative area. Those kickers that I put on there created it. I don't run thermostats. The one on the left is a pressure balanced racing thermostat. The second one from the left is a regular thermostat. Both of them are 190 degrees. The two right ones are restrictor discs. Most racing cars run restrictor disc. That way you don't have a chance of a hung radiator and burning the motor up. The drawback is it takes a little bit longer to get the motor up to temperature. The positive side of it is you never have a hung thermostat. The trick is getting the exact right size. My airplane is somewhere between those two sizes. The block is a Ford Motorsports all aluminum racing block. As you can see right here, it has screw-in freeze plugs, not drive-in freeze plugs. Virtually no chance of a freeze plug blowing out. You can see that the engine mount is 1-inch 065 tubing. The rear mount uses a Moog chassis item. I think it was a transmission mount off a Chevy Blazer. You see the finned area that goes around my oil cooler. That helps carry heat away. I did have some oil temperature problems initially, but I resolved those through several things. You also see the bracket that holds the muffler up. That is a flexible bracket that keeps the muffler from being rigid. On the engine mount, there's several ways to set it up. I set my engine mount up so it was 1.5 degrees nose down, and the engine is canted in the airplane 1 degree to the right. In hindsight, I wish I would have put the engine 2 degrees down and 1.5 degrees to the right. The right's not bad. I just make it up with right rudder on takeoff. I'm running a carbon fiber propeller. They're great propellers. The problem is the leading edge is very fragile. You can't see it much in this picture, but this engine will suck up any rock within 50 feet of it, and it nicks the leading edge. When you build your cowling for your airplane, you want to leave yourself a pretty good size access hole to get in there to change the oil or check the oil, and to add oil if you have to, and to check the coolant levels. This is the front nostril of the cowling, and inside there sits the beast. It's a 302 block, bored and stroked for 347 cubic inches, all aluminum V8 Ford. This is the right nostril. The fitting you see right there is something I fabricated later. This is the last addition, and this works just fine. That feeds my oil cooler. Another angle of it. And I machined everything in-house. That started with a 3-inch diameter solid piece of 6061 T6 aluminum. My oil cooler is on the side. I used louvers to discharge it. I ended up with an 1.5 by 7 by 12 inch long racing oil cooler. I've had 6 different coolers on it. This one seems to work the best. This is the discharge side of it. The louvers are canted back about 60 degrees to the airflow, and it gives me just enough suction to get the air out of the cooler without creating too much drag. The knock vents originally fed the cooler, but knock vents aren't very good at feeding pressure air into a closed, confined plenum, so that right there blows air on top of the oil filter itself that has those finned heat exchangers on it. Left side of the motor, some of these shots I just take so you can sit there and zoom in and look and see what I did. The left front nostril with the top cowling off, you can see a low profile air cleaner that I built, and on the firewall, if you look way back, you can see the Moroso expansion tank just out of the picture right there. The top left breather on the valve cover is where I put the oil in. Right side of the motor, same thing. Aluminum valve covers. I'm running a Holley 2-barrel 500 CFM carburetor with the McNeely mixture block. I'll explain about the mixture block in a little bit. Top view. You can pretty much see how everything's laid out. Try to keep it as logical and as functional and simple as possible. That's a belted air redrive on the front that I modified to fit a Ford, and then modified it several times after that to absorb the horsepower. This is going to be a pretty long detailed shot of the left side of the motor. I'm going to go ahead and let it sit here for a while so you guys can look close at it if you have any questions. It's pretty much self-explanatory. Redrives in the front. I built my own mounts. That's 1" 065 chromoly tubing. What I'm pointing out now is the sensor for the EGT that is in the collector. All 4 pipes merge into the collector, and so the reading that I use in my EGT is hotter. I just pointed to where you check the oil. I'm pointing to now where the Moroso expansion tank is, where you put the coolant in. When you mount it on a liquid-cooled engine, keep that tank as high as possible to get the air bubbles out of the motor. Don't try to put it below the water level of the motor. You'll be fighting it. That's where the oil goes in when you have to add oil. This motor will run 50 or 60 hours, and I never even have to add a half a quart to it. It's just a nice, tight, sealed up, liquid-cooled 347 cubic inch motor. That is the water temperature sending unit that goes into the intake manifold itself. As you can see later in my instrument panel, I have 3 different water temperature senders from 3 different locations. That one is actual true temperature of the motor itself. This other sensor is the one that actually comes on the way between the engine to the intake to the radiator. So I have a slight temperature differential between those two. I originally did that if I was going to run a thermostat, that if you did have a hung thermostat, the difference between those 2 readings would show a hung thermostat. This is the front of the block. It's a Ford race parts block. It's a Skunk Works division of Ford that builds this block. You can't call Ford and get it. They'll claim they don't make an aluminum V8 302 block. This is the right side of the motor showing the plumbing and the oil cooler sitting right there. My ignition system is MSD. I have dual ignitions, dual MSD boxes, and a coil switcher. It's all mounted on an aluminum plate, and that aluminum plate floats with vibration isolators. Instead of isolating each component, the whole electrical system sits on a plate and the whole electrical system floats. That is the MSD coil switcher. So you feed it 2 coil inputs. It has 1 coil output, and that 1 coil output goes to a custom Mallory distributor, which is actually a dual pickup distributor. The MSD boxes are actually 6 ALs, not the 6 A's. The ALs actually let you put a RPM limiting chip in it. This motor has got 4,500 RPM chips in it, so in case anything happens, it can't overspeed and break the prop. The distributor, I ended up with a Mallory billet dual point or dual pickup distributor. It's a lot smaller than the MSD I started with, and it's a lot better of a distributor and competitively priced. I was very dissatisfied with the MSD distributor that I started with. This is it right here. It's a lot bigger of a unit in dimension. It's pretty well constructed, except dimensionally it's just hard to put air cleaners around it, and it takes up a lot of the space where the water discharge outlet is, or the thermostat housing. The other problem is it came with a soft gear, which you have to run when you run roller billet aluminum or billet steel camshafts. The problem is the material that they used was too soft, and if you look at the top gear, you can see that's a brand new one. The bottom gear, after 10 hours of use, it shaved those helical cut gears to a razor thin edge. Right where it's pointing right now is razor thin. It wore out. I ended up calling Crane Cams and having them custom build me a gear to go with the camshaft I had them built for me, and it's been running fine ever since. This is the right side of the motor in the front. That's the belted air redrive that's been modified. Do not use a redrive that does not have a lower outboard crank bearing support. There's a tremendous amount of pressure on that crankshaft when the motor loads up, and without that support you would for sure break the end of the crankshaft off. As you can tell, that's a custom-made flywheel I built, and on this particular motor I decided to run an externally balanced motor. My motor mounts are a Moog chassis item, and if anybody that's real sharp can look at that motor mount right there, that happens to be the front I-beam suspension off an F-Series Ford pickup truck. Works absolutely wonderful, easy to adapt, and more than durable to hold that engine. There's 6 engine pickup or mount pickup points on this engine. That's one of 6. Here's the side view of the redrive. One of the failure points that I had originally. The redrive came with a 1/2-inch block plate, which fit a Chevy, which I had to make for fit a Ford. The front plate started out 3/8, and you can see right here there's a 200 thousandths clearance between the lower sprocket and the end plate itself. What happens is when you load the belt up and give it full power, that front plate that I'm touching right now did curl in and hit the lower sprocket. I couldn't believe it either, but it did. So I manufactured a 1/2-inch front plate, redid the lower bearing mount, and put spacers in so it would completely locate it so it couldn't curl in. Here is the original 3/8 belted air redrive front plate. Looks stout, doesn't it? Under full power applications, the bottom of that plate curled all the way over 200 thousandths of an inch and actually hit the lower sprocket. Right where I'm going to point at right there. Hard to believe, but it did. There's a tremendous amount of force when you run full power for that belt trying to shrink the center of that lower shaft to the center of the top. I've been through several different belts. I've had the best luck with the Gates Polygrip GT belt. This is a 966, 85 millimeter wide. Good luck with that belt. Another thing that I've had a problem with is the lower sprocket is kind of hollow. He built it to adapt to a V6 Chevrolet and a V8 aluminum Oldsmobile, and the sprocket's basically hollow. I'm trying to have somebody right now custom build me a lower sprocket that's solid, not hollow. When this thing loads up, the lower sprocket deforms just slightly, and the belt walks from the back to the front. Not much, but it does. Here's the custom front plate I built on a Chevrolet. The starter bolts to the pan rail. You don't have to worry about it. On a Ford, you have to bolt the starter to the transmission, and in this case, that would be the front plate of the engine. I use a reduction drive starter. It's a rowdy little unit, and this starter is very light, very powerful, and very economical. This is the original front plate, block plate for the V6 Chevrolet. You can barely see it. That had to be changed and turned into a 1/2-inch plate. These are the parts that came with the belted air redrive for a V6 Chevrolet. That's the bearing for the top shaft. The leather bearing is the lower shaft. My Ivo prop is an electric in-flight adjustable. This is the arm that I fabricated to hold the brush assembly on to the commutator so you can transfer power and make the prop go from fine to coarse pitch. The McNeely mixture block actually goes on a Holley carburetor, and it works just so slick. I mean, it's the nicest thing I think I bought on the whole installation. How he builds it for the price, I'll never know. But you take the carburetor apart, you take out the metering block, you replace it with the McNeely mixture block, you put it back together, and you adjust the arm and hook it to your mixture control valve in the cockpit itself. That's full off, that's full rich. I can go anywhere from idle cutoff to almost 30 gallons an hour of fuel. Very nice, well-built part. Two things in this picture. This is the return line coming back from the radiator, so to give me the water temperature just before it enters into the water pump. And I also run a harmonic dampener, and I don't believe in the rubber mount. I believe in the fluid-filled harmonic dampeners. It weighs a little more, but it's very effective. Here's the alternator and the lower bracket that holds the alternator on. This picture shows the transducer for the JPI fuel flow sensor. That in itself works real good. Here's my cockpit, interior, And in a minute I'm going to talk about the gauges. You're going to have to bear with me. My gauges are kind of complex, but they're engine documentation since this is a one-of-a-kind application. As we go along, top left gauge is going to be engine RPM. This is not prop RPM. This is engine RPM. I usually take off at 4,400 RPM and cruise at about 3,000. Next gauge down is going to be oil pressure. All my gauges in this airplane are mechanical. I believe in mechanical gauges because they're 270-degree sweep and they stay active even with the power off. Lower gauge down there was oil temperature. Then my first gauge is engine water temperature. That's right by the thermostat housing. Second gauge is the one that's just before the radiator. The third gauge shows the temperature of the water coming back from the radiator just before it gets to the water pump of the engine. Fuel PSI. I run about 5 PSI on the Holley. I'm a firm believer in manifold vacuum instead of manifold pressure gauges, and I'll tell you why in a minute. Unshunted ammeter gauge, EGTs, and I run a real hot EGT on takeoff. I'm pushing 1650, almost 1700 degrees on takeoff. Airplane's coming up on 200 hours, and it's made it back to the airport every time. There's been a couple things that have scared me, but nothing has prevented the airplane from landing back at the airport it took off from. So I guess I'm lucky. Now, as you look through the bottom gauges, I'll explain. The reason I like the manifold vacuum gauge over the manifold pressure gauge is that if you have carburetor ice, you can go to full throttle. If that manifold vacuum gauge, when you're at full throttle, doesn't go all the way to zero, then you know that you have an obstruction in the carburetor, which is carburetor ice. A manifold vacuum gauge won't tell you that. If with full throttle, you have to know what your outside pressure is, and that's hard to figure out based on altitude. Center stack of it is a navigation and communication. The top one is King KMD 150 multifunctional display, ICOM 200 radio, transponder, PS Engineering intercom, start switch, ignition, double pole, double throw switch, 2 fuel gauges, prop, double pole, double throw, flaps, double pole, double throw, external ELT, which is required, suction gauge for the gauges, my JPI 450 fuel flow gauge, which I conveniently mounted right next to the mixture knob, so you just have to look down when you turn the mixture and stare at the gauge and you can check your fuel flows. As you can clearly see, my situation is unique than most because as the airplane sits in the hangar right now, we're almost 7,000 feet above sea level. This is the KMD 150. I've turned the panel all the way up, dimmed all the lights in the hangar as best I can, and this is the panel fully lit up as well as it can show up on a video. Airplane is real slow, lands at about 45 miles an hour, VNE's 150. Plane is so aerodynamically dirty, I have pointed it straight at the ground, kept it wide open, and I can barely get to 140 miles an hour. Underneath the instrument panel is this hot rod radiator, aftermarket radiator that uses engine coolant. And what this thing does is put out about 40,000 BTUs, and it keeps the cabin at about 70 degrees when it's 20 degrees below zero outside. Real simple, real light unit, and it works real fine. This picture basically shows just how compact my power plant is. You can look how much smaller the footprint of the power plant is in relation to my firewall. And the reason I did this is I wanted to fit as many applications as possible. The Bearcat, the RB10. The Chevrolet engine is probably it's good engine. It's dimensionally about 25% bigger. So by going with the Ford with the shorter block, I can fit more airframes using the Ford 302 Windsor style than I can a 350 small block Chevrolet. All three sides, you can clearly see that the cowling itself is a lot bigger than the power plant package. I used a Franklin 220 cowling, and I probably could have custom made my own that was a little smaller, but I didn't think it needed it. So as you go through your building process, you have to look at your mission. Do you want to go fast? Or do you want something slow with a short takeoff and landing that's very tough for backcountry strips? I have my own private airstrip. It's located at 8,000 feet above sea level, just about 38 miles from Jackson Hole Airport, where I'm at right now. That's why I picked the Zenith 801. It's a nice airplane. They're great to do business with. I highly suggest that if you are in the market for a STOL airplane, you pick this one, but you have to do some soul searching and decide, because this plane is not fast. Appreciate you watching. I hope I answered some of your questions. If you have any additional questions, you can feel free to contact me at www.hosspowerair.com, and I'll be more than happy to answer any question that you have. And I feel like if you think things through, you should be successful at whatever you do. Just remember that it has to be done right.